Hi, I'm Fernando Pereira from UFMG, and today we shall talk about how to recognize natural loops within control flow graphs. We start this class revisiting the notion of a natural loop. As we had seen in the previous class, a natural loop is just a strong component in the CFG with just one entry point. We call this entry point node age, meaning header node. And now we look into this problem. How to distinguish two natural loops in a strong component? More yet, how to separate them into outer loop and inner loop? Remember, in a strong component, we have a cycle. So, from any node in the nested loop, we can arrive at any node in the outer loop. Anyways, would you like to think about this question? How to identify a natural loop nested into another natural loop? To identify natural loops, basically we need to identify their header nodes. Given that a loop can only have one header node, by finding this vertex, we find the loop. Now, to find the headers, we shall use the notion of dominance. That's one of the most important concepts in static analysis, so pay attention. In a directed graph with a starting node, we say that D dominates N if every path from this starting node to N must go through D. And we can find all the dominators of a node using these two equations. The first explains how to initialize the set of dominators of the starting node. The other iterates to a fixed point. We shall discuss it later. Notice that a node dominates itself, and that the only dominator of the starting node must thus be itself. About the other nodes, we initialize their dominance set with all the other nodes in the CFG. No worries, if you look into the second equation here, you will see that it uses intersection. In other words, the dominators of a node are the node itself plus the intersection of the dominators of its predecessors. So intersection naturally prunes away the initial dominator sets. This analysis that we are using to find dominators is thus a must analysis. Let's see how we can find dominators using this example. Before we start, can you check if the CFG is reducible or not? Anyways, let's start with nodes A and B. What are the dominators of these nodes? You can stop the video to answer the question. The dominator of A is A itself. Because, well, it's not really the starting node, but almost there. And the dominators of B are B itself, naturally, plus A, the intersection of the dominator of the dominant sets. In this case, gives A because the dominant sets of nodes C and D, which are predecessors of B, contain all the other nodes, but the dominant set of A contains only A itself. Remember how we initialize the nodes. We initialize them with all the other nodes in the CFG. At this point, would you like to answer the question in the gray box? Again, you can stop the video to do it. Before we move on, I recommend you to stop the video again and make sure that you understand how we've computed the dominators of C, D, E, and F. Now try to think about the dominators of G and J. What are they? Let's look into the dominators of J. This set contains J itself, plus the intersection of the dominators of E and F. This intersection yields A, B, and D. Now try to figure out what are the dominators of H, I, and K. And finally, can you try to find the dominators of node L? That's the latest node in our CFG. I hope you remember by now how the dominance equations work. And here they are, the dominators of L and of every other node in the CFG for that matter. From the notion of dominance, we can define the notion of immediate dominance. The immediate dominator of a node n, which we call idom of n, is like the closest dominator. It's the closest dominator of the node, I mean. In other words, if n has any other dominator, then this other dominator also dominates the idom. Something very important is that the idom is unique. Can you try to figure out why? In other words, can you try to prove this theorem that I have stated here? Go ahead and stop the video. Try to think about it. Here's the reasoning. If neither D nor E dominate each other, then there must be a path from the beginning of the graph to N that does not pass by one of these dominators, I mean D or E. Just look to this figure on the bottom and make sure that you understand why this is true. So let's see some examples of immediate dominance using the CFG that we had seen before. Can you guess what are the dominators of J and L? What about the other nodes in this CFG? Can you find their immediate dominators? Here's a table of immediate dominators. Each node, except the first node in the CFG, I mean, the starting node, has a unique immediate dominator. The starting node doesn't have a dominator. And if the dominator, the immediate dominator, is unique, and every node has one except for the starting node, then we can build a tree with these dominators, immediate dominators, I mean. This tree will be rooted at a starting node. For instance, can you figure out the dominator tree of the CFG? Just one thing before we move on. Some people say dominance tree and others say dominator tree. It does not matter. You can use any one of these terms. Here's the dominator tree of our example CFG. And now that we know everything about dominance, we can identify natural loops and nesting relations between loops. Can you think about it? How does dominance let us tell when a natural loop lays nested within another? Let's first define what's a back edge. We say that a back edge is an edge from a node n to another node h, such that h dominates n. So every node that's the target of a back edge is the header vertex of a natural loop, assuming that we are talking about a reducible CFG. So can you find the back edges and natural loops in the CFG? We have 4 natural loops in the CFG, one for each back edge. This observation that back edges determine natural loops gives us then the means to find all the header nodes in a CFG. Basically, a node H is a header node if there is a node N in the CFG, such that H dominates N, and there is an edge from N to H. This edge is a back edge. Notice that we can have H and N being the same node, and the definition is still good. Is the CFG. In the CFG on the right, can you spot which nodes are loop headers? Here they are, painted in gray. We have 3 loop headers, but 4 natural loops, as we had seen before in the CFG. Now, before we move on, can you think why these notions of dominance, header nodes, and back edges only work for reducible CFGs? I'll not be answering this question actually in this video. So either you think about it, or you will have to ask in our news group. Now for the last question that we still need to answer. How to know if a natural loop is nested within another loop? Basically, if a strong connected component contains 2 different loop headers and one of them dominates the other, then we have a nested loop. Remember, the CFG must be reducible and every loop is natural. Then the dominating header defines the outer loop, and the dominated header defines the inner loop. But one question, before we are done. Is it possible that no header will dominate each other within a strongly connected component in a reducible CFG? Think about it. Well, here's an answer, and it's perfectly possible. We have that A and C are both loop headers within a strongly connected component, and none of them dominates the other. But they must be necessarily nested within an outermost loop. And that closes our class on natural loops. Next time, we shall talk about some loop optimizations. Till then, feel free to write me with questions or comments. Thank you.